This is a systems engineering talk as well as a security headers talk. First, Wes is going to introduce TLS stripping and man-in-the-middle attacks. He's going to show off a technique and a tool that he created to demo why strict transport security is important. And then we'll discuss the concept of HSTS, the importance of preload. Who knows HSTS? Okay, good. So we assume knowledge of like general man-in-the-middle attacks, of HTTP headers, of TLS, so we can skip over that. But this feeds the question when we were doing research is what is the current state of strict transport security and HSTS adoption across the internet? As far as we know, this hasn't really been done since 2019. So in order to do that, though, we had to create something to do that kind of analysis at scale. And so to answer that question, I created a tool. It's not a hacking tool. It's a do arbitrary things fast and cheap machine. We're really excited to share it. We made the repo public, so that's going to be available on the last slide of this talk. So this is a framework that's tuned for network latency. We analyzed the top 1 million domains for HSTS adoption and preload. And then after introducing the tool, we'll share results and some really cool gems that we found out there on the internet. As y'all know, the internet is weird. The internet is weird. We found some weird stuff just in the strict transport security header, and we're looking forward to do more research in the future. So let's go ahead and get started. Go ahead, Wes.
Am I on? Cool. My name's Wes. Go by Oberlin. I like coffee, burritos, and stuff. A little about me. This is my first talk ever, so if I mess up, it's bound to happen. So you guys are already my favorite people. So as Hoop said, this is it's a header talk, but we're really going to focus on just the craziness out there, the relationship that we should have as pen testers, offensive people with dev teams. But every good story deserves a good origin story. So why did we start doing this? Well, it really came down to TLS stripping. Shout out to Moxie Marlin Spike, gave an awesome talk in 2009 at Black Hat about SSL stripping at the time. If you're still worried about SSL stuff today, you probably should change things. But just a quick overview of what it is. It's going to involve a man-in-the-middle attack. When I say man-in-the-middle, ways that the attacker is going to really hit this is going to be through ARP spoofing, DNS hijacking, and rogue access points. If anybody's friends with Daniel C on LinkedIn, don't tell him I said public Wi-Fi is scary, please. The way it goes, the victim is going to somehow go to a website unencrypted at HTTP. This could be through social engineering or just from the Ask Jeeves days, and you're pounding your head to go HTTP://. They'll send a GET request. At this point, the attacker's already on your network. They're going to capture that, add kind of a proxy, and then they're going to send that over to the server. And the server is going to do its cool little dance, the 301 redirect, make sure it gets a secured connection. And then at that point, when it comes back, the hacker is then going to downgrade that, and this is where the stripping comes in, and send that back to the victim. At this point, everybody's happy. The victim's website is working, they're able to load up stuff, the attacker is getting all the information, the server has its required secure connection. Why is this dangerous? Well, many reasons. One reason, if you log in, the victim's going to send the credentials. Well, the attacker is going to be able to see it. And as you'll see in my next thing, you can actually capture the PCAP file. And there's awesome stories I'd love to tell you about my BDP experiences with that. But at this point, the attacker can then drop the connection, leave, I have your credentials, or they can keep playing it. They go forward, they come back, they can do website defacements. They basically own the victim right now. So, since it's my first talk ever, why not tempt the demo gods? So, when I first started doing this, I really was interested in, hey, I've never really done a man-in-the-middle attack. And so I spent hours at home playing with different hardwares, like messing up our internet, getting yelled at by my wife. So it was fun to do ARP spoofing. I highly recommend everybody else go do it. It's a cool learning experience, but I really wanted something simple. I didn't care about the man-in-the-middle attack anymore. I really wanted to see what the victim was seeing, or what they weren't seeing. So I used the tool BetterCap. It's a pretty sweet tool. I know I talked about Marlon Spike. He has SSL stripping. I personally think BetterCap was better for me. I'm not really a developer, so it did everything I needed. And I incorporated the Linux namespace. So I essentially created a hostile network on my laptop with an isolated browser that would act as a victim. And now I could see what the victim's doing, or if I really want to get in the man in the middle, I could see the PCAP file or see what they're doing. So before I kick it off, I'm going to hit 2 websites, and we're going to see what the victim sees. But I want a baseline. So the first website I'm going to hit looks like this. So keep a mental image of this website. All right, let me kick off. So when I load this is the BetterCap file. So if I'm the attacker, this is where I'm going to play with. But really, we're focused on the victim. Victim logs in. They decide to go to this cool website, bitedogcyber.com, because maybe it's going to give them stuff. Sorry, talk to that. See, come here. And they go. Takes a second just because of how it's working. Bam. Deface the website. And I just showed the defacement because I just wanted to keep it simple. There is a better PCAP file created that you could go and play, and we have this out on GitHub. You can go play around. But this is just showing this is what the victim's going to see. And now let's say the attacker. So we saw what's bad. Website, not good. Let's see what a good website is. And one would expect that a hacking conference would have a good setup on their website. And so you get tricked to go into it, and lo and behold, it doesn't strip. So Wild West Hacking Fest, round of applause for them because they actually did it good. So what's happening? We saw it's the same network, same browser, same tool, same attack, same everything. The only difference is something happened in the background. What happened in the background? And that's where HTTP strict transport security happens. This is a header. It's browser security. It's browser security because it's a server giving a header, which turns into a rule for each browser to follow. The way it works, let's take the attacker out of the way. The victim now goes to the website, HTTP, or they just type it in, and Chrome's really good at upgrading you if you just type in without anything. But they'll send the GET requests. At this point, everybody's familiar with a 301. It's going to say, nope, we need it secured. So it'll send it back. But this time, the server is going to say, hey, take this cool little doggy bag. It has HSTS in it. And from here on out, anytime you ever see this domain and it's talking to the browser, don't even attempt to send unencrypted. I don't want to see HTTP, only the S. Cool, so he's had it. This is cached in the browser at this point. The victim then later goes back the next day. They do the same thing. This time the browser itself rejects it because it knows the server does not like this. As you can see, the connection at this point is never going to hit the server. And then it does a 307. This is an internal redirect, and then it sends it. So what exactly does the browser or does the header look like? What are the rules that the server is telling it? Well, strict transport security is the actual header name. You're going to see a max age. This is telling it, hey, cache this in your browser for this amount of times. We'll see later, and it's in seconds, so 1 year is kind of like what you should really be aiming for. And then include subdomains. There's so many subdomains nowadays, it's so easy to create a website or add stuff to it. So obviously you want everything covered. So as long as you go to a domain once, you should be covered for the X amount of time. But what happens? What happened on the second one, the Wild West hacking things? That was the first time we visited. At no point were we ever making that interaction to get that cache. Well, that's where the super cool preload directive comes in. This preloads it to the website. Now it's hard-coded into the website. It's ran by the Chromium project, and all major browsers pull from it. Whenever they release a new browser, it's going to be hard-coded in there. So at no point do you ever need to make that first connection. Every single browser already knows you're there, which is pretty sweet. And so why didn't I do that on my website, the one that failed? It's so easy. You just put up preload. Well, funny story, I did. So the very top header is Wild West Hacking Fest. As you can see, it has the max age, include subdomains, and preload. On my website, the bottom that failed also has max age, subdomain, and preload. What happened? Where's the issue here? As you can see, there's blue boxes up there. The top one obviously says it's preload. The bottom one says it's eligible for preload, but it's not. where did I get that? And this is where it started getting funny. And I was new to HSTS. I was junior web app tester. And so I started looking, found out there's actually this website called hstspreload.org. It looks like it was made back in the 90s, but it's still very, 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 very awesome. On this website, it gives you all the requirements you need to do to preload. And so far, we're meeting all the requirements. One that I haven't added, the very first redirect your website needs to make is to HTTPS. So not from like base to www. Example. Remember, www is a subdomain. So, cool. But I was missing one thing, and this is the important thing, and this is where conversations, I think, when we talk to developers and things like that, they really need to understand things that they're implementing, because there was one easy third step that I missed. It's literally a form. You type in your domain, it'll research, say, hey, you're eligible for it, you're on it, you're not. And if you go to mine, it'll say, hey, you're eligible, but you're not preloaded. You literally click a button, preload it, and then the next release iteration is gonna have it. So that's where things really, really got interesting, because when I was going out researching, just trying to strip as many websites as I could, I saw the ByteDogs website as the most consistent one. Everybody had some type of HSTS preload header on it, but most of them didn't. And then we got to talking. We're like, how bad is it out there? So he's like, let's scan the internet. And we learned some cool things. You're gonna see some pretty awesome things. And I hope this just gives you a little base about HSTS. But what we really learned was headers don't fail loudly. They fail quietly and at scale.
Yeah, thanks, Wes.
Yeah.
So our problem statement was we didn't just want to limit ourselves to HSTS. We didn't want to limit ourselves to HTTP headers. We wanted to build something that could do arbitrary things at scale, right? Because we're not just going to stop here. Yeah, this is fun and this is cool and we did a deep dive, but we want to be able to do other things good too, right? So why 1 million domains? We wanted to look at the top 1 million. Why 1 million? Because if we're being real, they account for well over 99% of all internet measurable web traffic. And again, we wanted it to do arbitrary things. So some of the key tenets were like, hey, jobs have to be parallel. We cannot serialize these things, or we'll be here for weeks, months, maybe, right? Depending on how big we want to go. The execution nodes, they got to spin up, and they got to go, and they got to be shut down, like closed down relatively quickly, because I'm not made of money. Anybody here made of money? No, we were doing this on a personal budget, right? And cost was a big thing, right? I don't have 40 servers that I can spin up in my basement. I don't have that time, the time and money to spin up all these cloud infrastructure and keep it running. We wanted to track the jobs from start to finish, and we really wanted to focus on throughput over latency. All of these things were network latent tasks, right? An HTTP connection is going to take on the order of like 50 milliseconds to a few seconds, depending on where you're going. The actual language we use didn't really matter, because we're like, what's the difference between 4 cycles and 200 computer cycles in the context of like a network connection that takes a couple seconds at most, right? So we wanted to run this user-defined computation across a dynamically scaling fleet of machines with minimal assumptions about what the actual job is. We wanted to maintain correctness and throughput as first-class goals, and we wanted to do this at internet scale and cheap as possible. So let's talk about the failures first. I failed a lot, if I'm being real. Like, I've been trying to do something like this. I've had this idea, said I wanted to do this kind of research for like 4 years since I started dabbling in programming and Python, and I failed, right? Like the first time I tried to do this, I tried to serialize everything. Bad idea. I didn't capture error handling, so like one error from like connection or just weird bytes that got from stuff maybe even being modified in transit. Like boom, my program would just throw up all over itself. It was terrible. Just like poor man with chili on the office floor over there. So I learned about like multi-threading, multi-processing, async event loops. Those were all possibilities for the concurrency. And then error handling was a huge thing, because at internet scale, as we learned in the Kubernetes workshop, like if you scale up, like is that feedback good for me?
Yeah.
All right. So if you scale up, like failures aren't exceptional anymore. At some point when you scale up, failures have to become the norm, right? So we have to handle that appropriately. And also the internet's weird. Even something as simple as parsing the HSTS string is not simple because people don't follow the RFC. Developers will just put whatever they want in there. Let me see if I can modify this a little bit. Oh yeah, and I got a multi-threaded solution working, and it was just having a pretty good throughput, like 100 requests a second coming from my home IP. But then I experienced the ISP DNS DOS. Anybody experience this at home? That's where your ISP just says, nope, you're doing naughty stuff. We're gonna turn off your DNS and just block all DNS traffic. It's like, oh great, my internet's not working. My wife got mad, and it was fine. It was fine. She was not working from home. It was fine. Not at the same time. In grad school, I did a project to try to implement some sort of engine that could do this kind of stuff, and it was cloud native. I incorporated like Azure App Services, serverless. Some of y'all might be thinking like, hey, maybe Lambda functions is a thing to think about, or Azure functions. And with the Cosmos NoSQL DB, that was awesome. It worked. It was fast. It all chained together, and there was a lot of interesting business logic there where it could just chain automatically. But in Azure specifically, the first million requests are free, and then it costs a lot of money. So like way more than EC2. So that was not an option for us due to cost. So let's talk about the design. Three major components of the project. The project's called News Team. That's a reference. We don't have to talk about that. But like Wes Mantooth, that's the Channel 9 News Team. That is the gRPC abstraction. So we have a protobuf, and that protobuf governs. Who knows RPC, generally what it is? Good. Okay, so that governs the schema for the communication between the server and the client. And gRPC itself is an awesome project run by Google. It abstracts a lot of the concurrency, which is nice. It has strong typing. And then this submodule abstracts the gRPC. It abstracts the MTLS that's occurring between the client and server to keep it reasonably secure. If you can hack my system, I'd love to hear about it, right? Like you probably can. And then in the middle, we have Ed Harkin. This is the manager. In a news team, Ed Harkin was the manager, right? So that's the resource manager. That's the abstraction for the cloud compute. I didn't want to necessarily pin myself to an AWS API or an Azure API or Google or whatever cloud provider. So we abstracted that away and created an API for, hey, let's spin up the infrastructure and let's tear it down. It also implements a health monitor. So if we do scale up to hundreds or thousands of nodes, it's having a constant gRPC ping to make sure it's still live. And if it's not, it'll spin it back down and replace it with another piece of infrastructure. Finally, the secret sauce of the project is jazz flute. That is an AI-generated image of a jazz flute. All of these are AI-generated, by the way. So this has to do with, this is the user-defined functions. This is the business logic, the stuff that's actually executing. So a domain expert has to go in and write a function in Python and say, hey, we want to do this thing. In our case, it was collecting HSTS headers. But in your case, it could be querying DNS, it could be vulnerability scanning, it could be just querying the internet. It doesn't matter, right? And that's served as a server-side function callback to the gRPC server. So it knows when it gets a job, it's going to execute this thing. It leverages both the Ed Harkin and Wes Mantooth. We treat the schema definition as a Python data class. This is cool. So I'll show you a little bit later. You, as a user, the administrator of this, you define a Python data class, a job request and a job response. What data do you need to kick off this job, and what data do you intend to get back from it? Run a shell script, and that automatically compiles the protobuf. It compiles the SQLite. In my case, it was SQLite, but it can compile the SQL definition schema. So all you have to do is define a Python data class, and then it generally handles it for you. Yeah, let's move on. This is the architecture. I'm not going to spend too long on it, but I do want to highlight. On the left side, you'll see the user-defined schema. That informs in our case, the SQLite DB. Again, that can be abstracted away into any SQL, any kind of data storage. You also don't have to use that. You could chain this idea, right? You get a job back and it triggers something else, arbitrary code, a different project, right? You can chain this with us. In our case, we just wanted to do our analysis from a local DB. If you do your analysis dynamically and you're trying to parse HSTS strings dynamically, as we'll see later, like some people put commas. Like to us, that's absurd. Like semicolons per the RFC are how you separate the directives. People put commas in there. It's like, that doesn't mean anything to a browser. Maybe they don't know that. Maybe they don't. Maybe they're just trying to be naughty on the internet. Who knows? The blue box there, that's what's happening on the client side. That's what's happening on your computer. We've got our control node. The user implements a producer. How do we feed the jobs in? A consumer. Once we get the jobs back, what do we do with it? In our case, we saved it in batches to a SQL database. They instantiate a client, and then they instantiate a resource manager. The resource manager spins up the cloud infra. The cloud infra spins up those ephemeral execution nodes in green, and those speak via gRPC between the client and them, and they go do the work, right? We like gRPC. We like that user-defined schema. We utilize async queues throughout here. This whole thing was implemented via async architecture. That's one big thing that I learned here. This project was not vibe coded, but I certainly did use it as more of like a surgical scalpel, like for things like implementing the MTLS with gRPC, for things like the auto generation script to transform the Python data class into the SQL schema and the proto file. I learned a lot about async programming architecture. So how many threads do you guys think this uses on the client? Yell it out.
That.
25. Who else? You guys? 10? Okay, that's reasonable, right? Anybody else want to guess?
Good.
0. That's a bold choice, sir. I don't know who said that. It's 1. We're using 1. So if you're familiar with the async programming architecture, JavaScript uses this. It's a really cool, there's a white paper, I think, from 2009 on it. It's old technology, but if you implement this correctly, what happens is the runtime iterates over an event loop, right? And instead of having the threads that are competing for resources, it's a single event loop and it's event-based. So when it sends off that network request, it can just wait on that event to come back. And once that comes back, then it knows, okay, I don't have to be idle. I can go ahead and action that thing. So this is single threaded right now. It's generally not a good idea to mix threads and async architecture, and this thing goes fast. Oh boy, it goes fast. And that was one of the successes of this project. I'm not going to spend too long on this slide either, but this is the general data flow. So we talked about the architecture, the data flow from job creation to job completion. We have a producer that is a user-defined function. In our case, we were taking names, domain names from a text file, right? We were submitting those as jobs with the submit API to the gRPC client. That client's going to talk to the server. There's a number of servers that we could talk to, and this is just using a basic round-robin scheme to pick which server. The server invokes the callback, which is, again, a user-defined function on the far side. That callback gets a return value. That return value is in the form of a job response. That job response gets passed back from server to client and then back to our consumer function. So that's generally the life cycle. Our consumer function took that result, put it in a database, fine and dandy. Let's talk results. This is the fun stuff. So 1 million domains, that means that we made 2 million requests, both to HTTP and HTTPS. It took 88 minutes on our fastest run, which is darn fast, right? We optimize. I ran this a few times to see how I can optimize it. 40 execution nodes to one client seemed to be the sweet spot for me running this at home from my home ISP connection, right? So I imagine if I'm running this in a cloud environment, it would be greater. 20 requests per second was all we needed on each server. And then there are 10 worker nodes on each server. But I suspect that we only needed 1. Of those 1 million domains, we had a bunch of errors, right? There are errors everywhere. Of course, this is on the internet. DNS errors, there was 178,000. TLS certificate errors, we did not ignore those. We just said, hey, those probably aren't secure anyway. So like, let's be real about those. That was 55,000, 8.3%. Connection errors, this was generally connections issues on the client, whether mismatched cipher versions, TLS handshakes, timeouts, stuff like that. It looks like one of my things got cut off, but 1.9K was the server errors. That's where the server's doing something funky, and maybe it just responds halfway or doesn't time out, something misconfigured there. More likely, it's really not supposed to be an HTTPS service consumable by a browser. It's just something else out there that we found on port 443. And then 5 gRPC errors. All right, so more results. Over the top 1 million domains, about 66.4% were serving HSTS, serving HTTPS, and of those serving HTTPS, 25% were using HSTS, which I thought was incredibly low. Yes, it's a security thing. Yes, developers know about this unless they go do research, unless somebody's taught them. But given that this strict transport security is everywhere on like the how-to guides for how to spin up a web server as a best practice, I thought that was very low. So of those serving HSTS, 20% of them were serving with the preload directive. And of those, 22.8% were actually preloaded in the preload JSON document that's shipped with all the browsers. This was really interesting, the bottom right. This is the preload eligible, meaning they do everything right, and you could submit them on the hstspreload.org, but they're not actually preloaded. So let's talk about that a second, because this was an attack Wesley and I concocted, was the preload DOS. Chromium doesn't care who you are when you submit the domain for preloaded. They rely on you, on the server, issuing that preload directive to say, yeah, we're eligible and we want to be preloaded. But there's a lot of people on the internet to just copy paste. Their organization policy says, hey, this is a best practice. And if you put preload in your strict transport security header, you better be serving HTTPS on every single domain inside and out. Because what's going to happen when it's preloaded? Chromium says, hey, you're eligible. We're going to ship it in the browser. We're going to bake it in. After that, browser updates come out. And then every single one of your insecure sites that's over HTTP, the certificate is wrong or expired, it's just not going to work. If you have HTTP inside your environment, it is going to break stuff, right, if you're not ready for that. So there are 13,000 domains that we identified as likely vulnerable to that. It's also possible they're just beginning to adopt HSTS, maybe. But given the low number of the things that are actually preloaded and the low adoption rate and the low change rate of that list, we think that it's about 13,000 that might be vulnerable to that. I declare HSTS, right? Everyone knows Michael Scott. Obviously, Michael Scott, everyone. So 34,000 domains said they were preloaded. Actually, they just wanted to say it in the header. Doesn't actually mean anything. We learned something really, really cool during this. So Wes is using his not so strict tool, and we were doing some manual analysis, going over some top domains to make sure that our collection was accurate. And one particular domain, we saw it should be vulnerable. It wasn't preloaded. It did not do the domain the redirects from the base domain to the HTTPS resource on the same base domain. It redirected to another subdomain. Everything that we saw said it should have been vulnerable. Did that with his tool. That was a really cool use case. But what was going on? So we did some about this thing called HTTPS resource record. Anybody heard of this? We learned about it. Someone has, yeah. It's actually widely adopted, and it's pretty cool. It is a DNS record that says it's a signal to the browser, and a lot of browsers like Chrome, Firefox, Edge, they will all abide by this, and they'll say, I'm going to do this DNS request first just to make sure, and that's a signal to the browser that, hey, we want HTTPS only, and don't try making the HTTP request, which is really cool. It's governed in RFC 9460. It also has some other suggestions for like what protocol version and some other stuff. This was a mitigating factor. However, who's ever been in the middle of DNS? So after that, Wes went ahead and built into his tool also a man-in-the-middle response for those DNS requests. So if for those that say, hey, DNS is my security, it's like that's a bad idea, right? His name is Brick, probably. So of the 834,000 domains, we found 150 actually there. It's a good mitigating control. However, absolutely do not rely on DNS. In order for this to be secure, what would we need to do?
Preload?
Yeah, preload, but from a DNS perspective. DNSSEC, yep, maybe DNS over HTTPS. This can be secure. However, I don't think there's wide adoption on those. Maybe we'll do that research later on. All right, let's talk about the weird stuff. This is the fun part. We saw so much weird stuff, and it was so much fun. So on the first one you can see there, might be a little bit too small. Somebody put a content security policy in their strict transport security header. Just demonstrates complete misunderstanding. At least 10 domains on the internet served no sniff. They're like, no, don't sniff my traffic, bro. Like, please. Anything to a browser. That is literally just a vestigial, is that the right word? Of like the Internet Explorer MIME type content sniffing. And they messed up the header. Yeah, two domains on the internet, like on please. Also doesn't mean anything. Yeah. All right, one particular developer thought 5 million years was a good idea for his life. I don't know if he was trying to overflow the integer or something, or she, right? Like, but that was weird. 20 sites out there, 20 domains, had preload in their strict transport security directive, which is like good and best practice. But can someone read the max age up there? Max age 0. Literally the opposite, right? They're saying turn off HSTS. Oh, but we want to be eligible for preload, right? And this one was interesting because that's the SSL store, which is a business that sells encryption certificates. Literally a security company. We had others on there, just a bunch of defaults, stuff that was copy pasted. Maybe we saw evidence that of like Nginx misconfiguration, stuff like that. This one was the most fun. Max age equals -1. I'm gonna go back in time and disable HSTS, right? Of course, browser. Yeah, it's garbage. The max age distribution was something that we set out to do, and this was not surprising. Of all of the HSTS directives, we took a look at the max age, and we figured it would be the most common. It was at 52%, 2 years at 13%. These are also recommended values by the HSTSpreload.org. We saw 6 months, we saw 3 months. 4% had, about 4% had a max age of 0, which again, invalidates the entire header. So I know our previous numbers included that as like serving HSTS, but it's literally the opposite. It just turns that off and removes that entry from the browser cache. 30 days, less than 1 day. There was, 1 day is a weird, and like one person had 1 second. So it's like, that's almost as bad as 0, but okay. And then a few 0.2% with 10 years plus. This concludes our presentation. Once again, I'm Cary Hooper, and this is Wesley McElhinny. On the top, you'll see we have GitHub to News Team, which is that distributed execution framework. We're going to be doing more work with that. The second link is the man-in-the-middle demo. That's where it takes advantage of the Linux namespaces to actually test out, is my domain vulnerable, or are other domains vulnerable, with an actual representation of BetterCap. And before we get into our things for our company we're hiring, I want everyone to give a round of applause to the conference organizers, because they've just been doing great. And thank you AV team, thank you everyone. Thanks for your attention. We work for Bank of America, and we like it. They're copper sponsored this year. Wes and I are on the pen testing team at Bank of America. We are hiring. We have 3 roles for my specific team. However, the Bank of America is hiring more talent. Come see us at the booth, and come talk to us afterwards if you just want to chat. This concludes our presentation. Thank you very much for your attention, guys.
So, Luke and Wesley, we have time for questions.
Yeah.
I'm not sure how you prefer to take them, formally or probably full.
Informally.
No. Let's answer questions up here. We've got a lot. Can I plug in and show the demo?
Yeah.
And we got a bonus demo for you guys. I'm just gonna run this thing so you can see how fast it is. Over 10K domains. But in the meantime, we can answer questions. Anybody have questions on the framework, headers, security, HTTP?
For those very non-standard headers like the CSV policy and the HST, does the browser just kind of say, okay, big call is it, or what does the browser do?
I saw sometimes the browser respect missing the max age, but it was never like a solid thing. Yeah.
The browser's supposed to disregard per RFC, but again, every browser, the major ones are just going to discard it if it's not exactly what it expects. Chrome, Firefox, Opera, Edge, all of those are just going to disregard, and it's going to be like it's not anything.
Is there any reason that you guys found that a developer would set the max age under a year in that second format, or is it just pure them misunderstanding how it actually works?
Yeah, so he showed there was a couple that were 3 months, 6 months. When you go to preload, if you go to the website, it actually tells you to like slowly start implementing it. It actually, there's even like a warning, like not everybody should do this unless you understand it. So I think that's why we saw the 3 months, 6 months. We don't know if those people forgot about HSTS, but I think that's the only reason we would see less than a year.
So the Chromium project recommends a slow rollout for good reasons, right? They recommend starting off with a max age of 300, which I think is 5 minutes. Thank you. And that's just to make sure nothing breaks, right? Like that's what you do in IT and in ops. Gotta make sure your stuff doesn't break, because HSTS does break things. Users don't know how to like click through that. They don't know how to type like this is unsafe. Anybody know about that? And look it up. Yeah, yeah. Well, yeah, sometimes, right? But yeah, like if you home lab, okay. Internet, it used to be a bad idea. Yeah. Oh, okay. I didn't know that. That's before my time. Thank you. Yeah. So the slow rollout is good. They recommend like 300 and then like a month and then 3 months. And then they're like, yeah, you're probably good for a year after that. So this is a demo. This is just extra. It spins up I got 5 EC2 instances spinning up. It's automatically preparing those nodes. Like I want to get a specific Python version because I'm being very specific, but you don't necessarily have to. It's running all of that in parallel in the background and concurrent. And then you'll see once it starts saving results to the database, that's the actual like execution. It's not just spinning up the infrastructure, but it's actually like collecting the results and saving them back. Any other questions? Yeah.
What's the total size of the database when you're done?
Oh, you mean like the amount of bytes?
Yeah.
I think it's 14. Is it 140 meg? No, it was like 14 megabytes. I think, Wes, wasn't it?
Yeah, I might have one.
It wasn't very large, so we didn't save all of the headers. We saved very specific. Oh, I can show you that too.
Yeah, 146
So
megs.
for this in particular example, let's go ahead and this is the data schema that we were. Oops. Can you guys see that? Can you see that? So this is the schema we were saving. All we give it the job was a protocol and a host name, and then we returned back whether an error occurred, the actual HSTS string, whether a redirect occurred, and we needed that redirect and the redirect string because we wanted to see, does it actually comply with preload behavior? Is it eligible to be preloaded? And we could have collected a lot more, but was it 140 megabytes?
146 was the last one I had, yeah.
146, and that's for 1 million domains, 2 million records in there.
I loved getting your updates as you ran it, like, oh, it's getting faster.
So that was the goal. We were impatient, and we did not have deep pockets. Therefore, this was a lot of fun to. Oh, and I didn't talk about cost. Anybody want to know how much it costs to run? Is that 5 minutes or? Oh, you want to know? Yeah. It's about $1.20 with this because the infrastructure is ephemeral. EC2 instances are relatively cheap. I was doing it programmatically, and they were just closing down immediately after. It may be up to $2, but like that makes it reasonable to do the top 10 million domains, right? It makes it reasonable to maybe I want to scan all IPv6 space, and if you do this smart and you're not just doing 4 billion jobs and you're actually like scanning first, it makes it very reasonable that we could transition to like, hey, all of IPv4, let's go ahead and figure this out. Did you have a question, Adam?
No, like
Travis?
Any domains that were surprising to you that were like well known?
Ooh.
I'm not about to name and shame. Google specifically was weird because they didn't follow any of their own like advice, but because they owned the preload, they just automatically like, hey, so they said, trust us, we're preloaded, we're good. So they didn't actually serve a lot of the headers or have the behavior.
Yeah.
Go ahead.
When this first started, you can actually submit subdomains specifically for the preload list, and there is a really famous company out of Washington, starts with an A, that did it. They had www.amazon.com, but AWS is not covered under it. So I don't think they had include subdomain or.
They have to, because I think the we like QDNs of some of the instances and some of the execution. So customers' boxes might be running, and then that would apply to the entire customer base. They didn't include subdomains.
That's fair.
Correct me if I'm wrong.
There's something, but hit me back up on LinkedIn or something.
Yeah.
There's one I hit that was weird like that, so maybe that was wrong.
There's a bunch. So when we started looking, we were surprised with how little this was actually adopted. We'd like to see more. We'd love to see more organizations actually preload or use, like Tony was talking about, having a different domain internally versus one externally. Then you could preload the external one. And if you're internal with all your developer stuff, like maybe you use a different internal only domain. That's a good idea.
Well, my browser respect HSTS from a non-standard web port, or is only over 443.
Oh yeah, that's a good question. So HSTS is per domain. So it doesn't matter what port. Whereas y'all know what an origin is, how a browser treats an origin. Origin is protocol, domain, port, tuple, and a lot of the same origin policy, right? Browser security model is based on that. This is per domain, which is really nice because it's widely applicable to the domain.
So if I hosted a web app on 443, I was talking about 8443, HSTS will be respected on both domains because it follows the policy.
That's right. It'll make a request. It'll get that strict transport security header back. It'll go into the cache, into the little like SQLite DB. It's not SQLite, but it'll go. The browser will remember it, and then you go to any other port for that same domain. Now, if you include subdomains, then it's any port on any subdomain of that base domain. So the demo, like this is, it's running in the background. As you can see, there's like a little heartbeat. We're at 10,000 records just from like hotel Wi-Fi. It's a lot of fun, and this will spin down soon. So you guys get to see what it looks like. It's obviously more verbose than it needs to be. We are excited about it. Any other questions before we break? Thanks for the awesome questions, guys. You were a great audience. Appreciate it.
Thanks, everyone.
Thank you.